Welcome. Today I'm going to be presenting on advanced time series prediction for buildings. This is part of my research at the University of Victoria, where I worked at a lab where we tried to optimize building design and building operations with machine learning. It is part of these two papers. The first paper, I used gradient boosted trees for surrogate modeling to great effect. They are a very accurate and efficient algorithm to make predictions from. When I was doing the second paper about time series prediction, at the time I didn't use gradient boosted trees, and that was one of the most constant points of feedback that came up, is how gradient boosted trees compare to neural nets for time series prediction in buildings. So this work today is meant to be a preview of the potential future work in this area. The data set I used for this work is an open source database from the Lawrence Berkeley National Laboratory. It's of Building 59. This is a recently built smart building that has all sorts of different streaming data available for a 4-year period. It has things like indoor air temperature, HVAC, mechanical, electricity draw, and occupancy. The two different features I chose to predict in this work were indoor temperature and the RTU flow rate. This is an overview of the 4 years of historical data. You can see on the right, the rooftop unit is much more noisy. There's also periods where the rooftop unit was either undergoing maintenance or the sensor wasn't working. The training involved in picking 8 different target dates equally spaced throughout 2 years and looking at the prior 5 weeks and then training in a 24-hour window. And basically the goal was to then try to predict the next 24 hours of the target feature. We also wanted to see how additional supplementary data affected the prediction capabilities. Here we have type 1, which is just mapping the target feature to the target feature. Type 2, we have the target feature, and we also add the outdoor weather. And the type 3, we map the target feature, outdoor weather, and time to the target feature. Including time there allows the machine learning models to pick up different types of weekly and daily patterns. This is an overview of the testing and training data for the rooftop unit and RTU below. There's many more training values, and that's what leads to a narrower probability density function. But here they're similar enough to continue with training. Now, I wanted to introduce the 4 different types of machine learning functions used in this comparison. First, we have a Gaussian process. And if I had to use the analogy of a building manager or operator, I would think of it as them sort of studying the historical data to make a probabilistic estimate as to the next value. Neural nets can only sort of uncover simple patterns. And so this would be like if the maintenance manager was looking at different trends just on a weekly or daily basis. A recurrent neural network also uses the historical data, but is much more powerful and can uncover much more complex patterns and trends. And lastly, there is gradient boosted trees. This I kind of imagine if the maintenance manager or building operator had a panel of experts, if they needed to make a prediction, they could then go to the expert to help make a more accurate estimate as to the next value. If you're looking for more information on gradient boosted trees, I have a whole video on how they work linked in the description to this video. Before training, I also undertook a hyperparameter search. This is so that when the comparison occurred, all the models would have sort of optimal parameters to perform well. You can see there that middle row sort of dictated which parameters were chosen. You can see the RNN, sort of a mid-sized network, had the lowest error. Neural networks that were only 1 layer deep showed good performance. For gradient boosted trees, only needed 2 trees to perform well. And for the Gaussian process, a linear kernel showed the lowest error rates. Here are the results from all the indoor temperature predictions for each 24-hour period on the target date. Already just visually, you can see the RNN sort of struggling to make accurate predictions. Moving to the flow rate, you can see that that noise again becomes much more difficult to predict. But again, the gradient boosted tree is really excelling at making predictions. Now we come to a series of scatter plots to illustrate the model's performance. You can see that type 1 there, the naive, is also included. And this is just a basic 6-hour moving average. And you can see quite a lot of dispersion along the diagonal. Across all three types of supplementary data, you can see that the gradient boosted trees is tightly clustered along that gradient, showing good model performance. Here we have a summary of the best and worst 24-hour predictions for the indoor temperature. I'll draw your attention to the gradient boosted tree there, which is doing an excellent job at predicting the target values. And of course, you can see the RNN really struggling there to make accurate predictions. Moving to the flow rate, again, the gradient boosted tree is really excelling here with even the Gaussian process struggling to predict this noisy data. And again, the neural net and RNN are sort of struggling to predict historical trends. Now we come to a summary of the overall performance. You can see there at type 1 on the left, the naive, which is just a 6-hour moving average, is really struggling to make accurate predictions. But the Gaussian process and gradient boosted trees is doing quite a good job. When you add more supplementary data, the neural net struggles a bit more, whereas the RNN does better. But again, the gradient boosted tree continues to do very well. Finally, adding even more data, now the neural net and RNN are getting quite confused. The Gaussian process has expanded in its air ever so slightly, but again, the gradient boosted tree doing a really good job and is very robust against all the different data types. When trying to illustrate how the data affects the accuracy of the model, the sort of the overall view doesn't show too many trends, but when you break them down by model, it's easy again to see that that gradient boosted tree is very robust across different types of data. Whereas when changing the amount of data available to the model, the neural net and RNN change quite drastically, with doing better sometimes with more data, as in the indoor RNN, but also sometimes the supplementary data tends to degrade the performance of the neural net. Now we come to some practical timing information for how long it takes to train and evaluate the model. RNN gets slower and slower the more information you are training on, whereas the Gaussian process and gradient boosted trees have very good training times. When you look at the evaluations, they're all nearly instantaneous, but Gaussian process and gradient boosted trees do take the longest to evaluate an inference on, and this might have implication if you're doing it at large scales. Hopefully, this comparison of different machine learning algorithms is helpful to people that need to make data-driven decisions about building data. Of course, we saw that gradient boosted trees are very robust across different data types, can be very accurate, and are computationally efficient. Finally, I just wanted to say thank you so much for watching.